All right, in this video, we're going to find Cartesian equations for, first of all, the locus of a circle in the complex plane. So for part A, we have the modulus of some set of complex numbers measured from a particular center, which is at 2i, or 2 plus I should say. And all those points have to be a distance of 3 from that particular center. So this is obviously a circle. The way we write a Cartesian form is to rewrite Z using X and Y components. So in other words, real and imaginary components separately. So I'm going to do that. So I'm going to write Z as X plus I, Y. And we still have the center to deal with. Now the center is at 2 plus I, but we write it as subtract 2, subtract I, and you'll see why that is in a moment. So all that is equal to 3. If you take the modulus of this particular set of points, it's equal to 3, which is the radius of the circle. Now, the next thing we need to do, now we've written Z as X plus IY, is we're going to collect the real and imaginary parts together. So the real parts is the X value there and the -2, or the X variable. The imaginary parts have the factor of I in them. So we've got the Y there and minus I there. We'll deal with that in a moment. So let's just sort out the real part first. So collect those together. And we have the modulus of X subtract 2. Okay, and to get the imaginary parts, let's just factor out the I. So we've got plus I multiplied by, and let's just write that as Y subtract 1 in there. Okay, close that bracket, close the modulus, and that's all equal to 3. So this defines a set of complex numbers, okay, in the same way. Now you'll notice we've got the real components and the imaginary components separately. That was our aim. Now this would be a distance along the real axis, okay, or the x-axis. Okay, it's an orthogonal coordinate system. Similarly, the y subtract 1 here would be a distance in the y direction, or the imaginary axis. So if it helps, we can think of this as a right angle triangle. So imagine we've got a distance x subtract 2 going along the real axis like that. And then in the imaginary direction, we're going up, or it could be down. We don't know. We don't know whether we're going left or right or up or down, but it doesn't matter. So we've got y subtract 1 in that direction. Okay, and the distance from this point here to this point has to be 3 units, because that's what's described over here. So let's do that. So let's just join up the right angle triangle. It is right angled, of course, because we're using X and Y coordinates here. So this is 3 units. And we can simply use Pythagoras' theorem to finish this off. So according to Pythagoras' theorem, if I take X subtract 2, square it, and if I add Y subtract 1 and square that, then we get 3 squared, which is of course 9, which is the radius squared. And you can see clear as day now that the center of the circle is going to be at the point with coordinates 2, 1. Okay, this was if it was in the XY plane, and we've got a radius of 3 here. Okay, so it describes the same thing, but in the complex plane. Now, moving on to part B, we have a different locus of points to describe. This time they're defined by an angle measured from a particular point where, as it happens, z plus 1 is equal to 0. If you're not sure what to do for this, if you just highlight this part inside the argument. And like we do in most cases, imagine that is set equal to 0. Okay. And then if we solve that equation, so if we solve the equation z plus 1 is equal to 0, this gives us the complex number z is equal to -1. So it's defined as a complex number, but in fact, it's on the real axis. It's just at the point with coordinates -1, 0, isn't it? Because it's got no imaginary part. Okay, so a good thing, again, it would be to draw an Argand diagram for this. So if I just draw the real axis there, okay, let's draw the imaginary axis going vertically. Okay, and we're going to label this point that I've just written down in red. So at -1, 0, that's the point we're interested in. Now, we've got this argument here. The argument, of course, is measured from the positive real axis, and we go either clockwise or anti-clockwise, depending on whether the argument is positive or negative, and it's only from 0 to pi in the positive direction. So a bit of revision there on that. Let's just draw this angle in. So it's pi over 4. Now, remember, that is, of course, 45 degrees, but we're using radians, so we'll write that as pi over 4. And we measure from the positive real axis. So there's the argument there. Now then, let's think about what this angle actually means in terms of a Cartesian coordinate system. Now, if I just draw a right angle triangle over here, well, that wasn't very good, was it? Let's try again. So if I draw a right angle triangle over here, like so, if this angle is pi over 4, which is 45 degrees, that means that if for every 1 unit I move along in the x direction, I must be moving 1 unit vertically in the y direction. This is a standard triangle that we use in trigonometry all the time, and it's got a hypotenuse of √2. But we just need to know the gradient. So we can see clearly here the gradient is just going to be the change in y, which is of course 1, divided by the change in x, which is 1 again, which is just going to be 1, which is great. Now that means we've got a gradient, and we've also got a point on the line. We've got this -1, 0 here. We've got this gradient here, so we can put it together and find a Cartesian equation of this line. So let's go ahead and do that. Okay, so if I use y equals mx plus c, so we've got y is equal to mx plus c. We'll just sub everything in. So y is, of course, 0 here. So 0 is equal to 1 multiplied by -1 plus c, the y-intercept. If I rearrange that, we are going to get c is equal to 1. Pretty obvious from the diagram as well. That is going to cut here at 1. So just to write down the Cartesian equation, we've got y is equal to x plus 1. All right, now notice we are writing a Cartesian form from an Argand diagram. This is a half-line argument. So technically this would only be defined really for y values greater than or equal to 0, although that is a technicality. The main gist of the question was just to get this part written down. Okay, but just bear that in mind, because the way the argument is defined, it has to be measured from the positive real axis.